Okay, so we're going to talk about distributed charges and the joy of the algebra that they bring with them. So normally we've been dealing with a single point charge, but now we're going to look at, well, what happens if we have more than one charge? I'm not talking like two next to each other. I'm talking an entire ring of charge. That's what we're going to start off with now, a ring of charge. Now we're going to make this positive, so there's a whole bunch of positives. Charge evenly distributed around this ring. By evenly, I did my best. And what we want to know is we were going to ask the question, what is the electric field strength at some point P located a given distance, call it X, away from the center of this ring? Now to do that, we're going to have to look at all the pieces. All right. So if we zoom in infinitely small, we would have like one electron. And so that would be a piece of the overall charge that this ring has. And each piece of charge creates its own electric field. So that electric field would interact and exist, pushing away because positives go away from each other, positive repel, positively charged test charge, blah, blah. So we would have a piece of the electric field pointing that way. Now, on the other side of the ring, there's going to be the same thing. We'll have a small piece of charge. That small piece of charge will interact at this location and have another, don't know what you're doing here, another piece of the electric field. Now, if we look at this, that's going to be true all the way around. We start making kind of our vector ring, if you will. And I can start breaking this down and say, well, you know what? In reality, these are two pieces. So I have DE in the X plane, and I also have a DE in the Y plane. And that would be true for this bottom one as well. Now, if we examine them even further, this one and this one are going to balance out because they're equal and opposite, creating equal and opposite fields, equal and opposite forces. It all cancels out. So DEY cancels due to symmetry. Now that's very important. We always want to see stuff cancel out. We want to see our mathematical lives get easier and easier. All right, so this is kind of like the setup. Let's include some more things. So we'll have some angle between these guys here. And let's call this radius A, and this distance away, we'll call that R. So we've got A, X, theta, and R. And what we really want to do is we want to get all of this in terms of X. I want to know how far away it is. Okay, so let's start seeing what we can see to find the overall electric field. So if we do this, we say, well, the electric field is equal to the sum of all the pieces of the electric field. Now, in this case, the only piece that matters is the X piece. And so I can expand that even further and say that is equal to dE times cosine of theta, because it is adjacent, so that's all we got to do. So now the question is, well, how do I go even further from there? Well, good point. So some things we want to keep in the back of our mind when we set this up. That's what I kind of started with here. The electric field is the sum of all the pieces, and that is also equal to KQ over R squared. So that means that DE is equal to K dQ over R squared. So I'm going to use those pieces to help me solve some problems. That's not what I wanted to do. That's what I want to do. So I've got my DE over here, and I'm going to replace that with this guy. So now I've got E equals the integral of K dQ over R squared times cosine of theta. Now, like I said, I don't want to have this in terms of theta. I want to get this in terms of r and x and a. I want to get these lengths out here. So a little side note, I say, well, I happen to remember that cosine of theta is equal to x over r, right? Because x is the adjacent, r is the hypotenuse. So, that's how we do things. So I can replace that with this guy. And when I do that, I then get the integral of k dq over r squared times x over r again. So really this becomes a cubed. All right, cool. All right. Now, next up, I don't really want r there either. So I can rearrange, I should say, relabel it as r is equal to x squared plus a squared to the 1/2. Now, why the 1/2? Because remember, Pythagoras said a squared plus b squared equals c squared. So here's my a, here's my b, and then r is my c. So basically this says the square root of x squared plus a squared. I just don't like square roots. It doesn't work well when you do calculus. I always get stuff into 1/2. And so I can replace r with that quantity. When I do that, I get k dq times x over the quantity x squared plus a squared to the 3/2, because it's to the 1/2 and then I cube it, so I get to the 3/2. So now I'm kind of good to go here, because now all I got to do is I got to pull out my constants. So when I pull out my constants, well, what are my constants? K is a constant, x is a constant, and a is a constant. So I get to pull all that stuff out. So now I get k x over x squared plus a squared to the 1/2 times the integral of dq. Oh, dq. Love those blizzards. Always bring me joy. Well, the integral of dq, that's pretty easy. That's just q. So therefore, the electric field at any point x away from the center of a ring that has radius a would be written as k qx, order's irrelevant, x squared plus a squared to the 3/2. So that would be our answer. Now, I always like to check myself. So here's a check. So check number 1. What is the electric field at x equals 0, aka center of ring? Well, we know that's 0, because at the center of the ring, all the charge, all the fields are going to balance out, because the total force acting on any point charge placed at the center would create balanced forces, all equidistant. We would have no charge. Well, that should be the answer. Let's see if that works. Well, if we put 0 in for x, all right, I'll go over here. If I just make that 0, 0 goes in the numerator, 0 divided by anything, 0 times anything, that's going to be 0. So we're going to be here doing that. That's totally checked, all good. Other check would be, what is the electric field at some point where x is really far away? All right, so that means x is going to be way bigger than a. So that means a is going to effectively go to 0. So if we make a 0, that kills that whole term. And then we get kqx over x squared to the 3/2, which is x cubed, which makes that guy die. That guy becomes a squared. Oh, look, we get kq over x squared, which is basically kq over r squared. So we know this checks out. That makes sense, because this right here is the equation that we were using as one of our fundamental concepts of the electric field. So Hopefully that helped you see how to derive the equations for the electric field at a distance when given a distributed charge, at least for a ring. We'll cover some other things. So yeah, come in and check us out. And until then, I'll see you guys in class.